In this video, we're going to try to go over the idea of activation energy. Now, activation energy is the energy that it requires to start a reaction. So many reactions are not actually spontaneous. They don't start on their own, and all reactions need a certain amount of energy. Spontaneous reaction is going to have enough energy from the environment to be able to overcome a low activation energy barrier. But lots of reactions require quite a bit of energy to even get started. So this is an exothermic reaction energy graph, and we've seen these before. And what we see is that the enthalpy is, change in enthalpy is negative. The energy is being given off because we are making more bonds than we're breaking. So the potential energy is going down of chemical potential energy. But you still need to break these reactant particles apart. So we need to take those bonds and separate them. And so it's going to take some energy to be able to break those bonds apart. And so this is broken bonds. And then we get that energy back. And then we get the energy change. So the enthalpy doesn't actually change. It's the same amount of energy, but it takes some energy to break some bonds, and then we get it back when we're making more bonds. So at the top here, we call this an activated complex. And the energy it takes to start the reaction is the activation energy. So this over here is the activation energy. We get it back, but it still takes that much energy to begin. If it didn't, this page would be burnt, right? Because it's an exothermic reaction and the oxygen is available, the paper is available, it will burn, but it requires energy to actually break those bonds. We actually have to start this with a spark or some heat to be able to make this burn. And so typically, those sorts of activation energy graphs, so this is an endothermic reaction, so it's delta H equals a positive energy, and this is delta H is negative energy because this is an exothermic graph. But to take my reactants in this, I need to actually put in more energy, and then I get it back to become the products. So my energy graph starts to look like that. And here, I have to put in energy to break the bonds, and then I get it back. And so an activation energy graph is going to look like this, or an enthalpy graph with activation energy looks like this. And the difference between the reactant energy and the activated complex is your enthalpy, or is your activation energy. And then the enthalpy is still the difference between the reactants and the products, right? So the enthalpy is unaffected by the activation energy, but we still have to add in this extra energy to break bonds in order to start the reaction. So activation energy is a sort of an important idea, and it goes back to the idea that we need to have the bonds colliding with enough energy and the right orientation to be able to break the reactant bonds and make the products, right? In a lot of exothermic reactions, once you start it, you don't need to keep giving energy because it's producing energy. So if I started burning the paper, I don't need to keep giving a spark because the heat from the exothermic reaction keeps the reaction going, but it still needed the activation energy to begin.